Vanakkam. Welcome to this video on biomedical instrumentation. We have been looking at various types of sensors. What are the various types of sensors that we looked at in the previous set of videos? So first, we started out with resistive sensors such as strain gauges. We discussed various types of strain gauges, foil strain gauges, different materials that are used, constant and nickel. And we said silicon strain gauges. What are the advantages, temperature sensitivity of these? Then we looked at thermistors, special negative temperature coefficient materials that have an exponential relationship with temperature and resistance. And then we looked at capacitive sensors that essentially exploit the epsilon A by D principle, in which one plate is a diaphragm that can deform, and the change in capacitance can be measured as a change in voltage across that capacitance, for example. Then we looked at inductive sensors. In particular, we focused a lot on LVDT, linear variable differential transformer type devices, and we discussed how these can be miniaturized and what are the various applications of these. Then we looked at piezoelectric sensors and the types of piezoelectric materials and what are the main applications of these. And then we looked at electrochemical sensors, ion selective electrodes, chemfets, biofets, gas sensors, etc. In this video, we will look at optical sensors and how do they work and what are their biomedical applications. So essentially, optical sensors exploit how light interacts with matter, in particular biological matter, in this case biological matter. And this interaction, the output of that interaction, if it's predictable, if it produces predictable results, then by looking at the results, we can come to conclusions about what is the matter. If we know what the input is, what is the wavelength of light, for example, and if I know what the output is, what the measured output is, then I could technically predict what is the property of the material, for example. And why is this useful? It is immediately obvious why this is useful, because I am interested, for example, in classifying, say, for example, between tumor tissue and healthy tissue, for example. And it is expected that the material property of the tumor tissue will be different from the material property of the healthy tissue. And we exploit the manner in which light interacts with these two different materials to produce different output spectra. So these sensors are so extraordinarily sensitive, very highly sensitive, and more importantly, they are non-invasive. They will not involve placing something inside. So we apply light from outside, we measure outside. So both the light source and the detector are outside the body. So they are non-invasive. That means that it is safe for biomedical use. Usually there is a light source, there is a filter, there is a path setup, and there is a light detector. In almost all the cases, the light source is an LED and the detector is a photodiode or a phototransistor. There are many applications for this. So most importantly, a critical advantage of using this system is they are immune to electromagnetic interference. So many of these can be used inside an MRI system. Not all though, many of these. Because light is insensitive to magnetic field, for example. And so they are nearly real time, in many cases real time, and they provide label free detection, and they can be miniaturized to a great extent, and many channels, many simultaneous measurements can be made, thus enabling us to multiplex this. So modern biomedical diagnostics and monitoring and therapeutic guidance use these principles to exploit and use optical sensors. Some of the applications that are discussed here are, for example, body fat estimation, oxygen saturation, and other biochemical analysis of various analytes of various fluids, for example. A governing principle in this field is Beer-Lambert's law. What is Beer-Lambert's law? This law states that when a ray of monochromatic light, the keyword there is monochromatic, when a ray of monochromatic light passes through an observing medium, the intensity of this is directly proportional to both the concentration of the observing medium and the path length of the light beam through the solution. Now, let's say that I am able to measure the incident intensity and the output intensity. Okay. And let us say that I have an idea of the molar observability and the path length, then I can technically identify what the concentration of the observing medium is. It turns out that this relationship is relatively linear for dilute solutions under ideal conditions. So quite often this is used for measuring oxygen saturation. During COVID time, this was a device that was used to measure what was the oxygen saturation in each. If the person is not able to breathe, they are having difficulty. This is a non-invasive device that was used to measure oxygen saturation. They were available relatively affordable devices. As to whether they were accurate or not, the jury is still out there. But this is the principle of operation. Again, this is something that you could open up and check how this is working. What is the principle of operation? Yes. So quite often these are used to determine oxygen saturation by comparing absorption at red and at IR wavelengths. And because I know the path length and I know the intensity of the input and the output, I could measure or estimate the concentration of oxygen, for example. Right? What are the various light sources that are used? What are the various sources of light? Tungsten lamps. But the problem is, earlier, Beer-Lambert's law, we said the monochromatic light. In this slide, we are saying tungsten lamp. But the problem is that these provide light at various wavelengths. So they are not suitable for monochromatic measurements, but they are suitable for visible and near infrared applications. Other sources are fluorescent and arc discharges. Once again, these are also, for example, argon mercury mixture, for example, which emits UV light. This then excites a phosphor coating, which produces visible light. Quite often, this is also used as a light source. LEDs or light emitting diodes are also used to power or to produce light source, to act as a light source in this case. And quite often in research and in many biomedical applications, lasers are used. Lasers stimulate atoms to emit light of a specific wavelength by the so-called process of stimulated emission. This light is then amplified and then emitted as a focused beam. These are the so-called monochromatic light sources. Quite often, these are the ones that are used in many biomedical applications. Also note that in cases where magnetic shielding is required, or in cases where there is a need to use this along with an MRI machine, we could use a fiber optic cable to send this light through the cable and then measure this at using a detector, and then amplify it outside the machine, and then process this. So there are these kinds of possibilities. Quite often we use fiber optic technology as a medium to transmit the input light or the output light from one place to another. So we know how fiber optic technology works. The details are beyond the scope of this course. Essentially, from our high school physics, we know that there is this Snell's law. What is this? Refractive index, two materials. If this fiber is made of two materials with two different refractive indices, n1 sine theta 1 is equal to n2 sine theta 2. The critical angle at which the refraction happens is given by n2 by n1. So if the ray of light is reflected internally for any angle above this critical angle, in almost all the cases, fiber optic sensors are replacing conventional sensors for measuring very many physiological parameters, because they are chemically stable and they are highly immune, or are almost always immune to electromagnetic interference. An advantage of these kind of another advancement in this field is the miniaturization approach to this. So with this, we will conclude our discussion on optical sensors. We will discuss Hall effect sensors and summarize in the next video. Thank you for your attention.